How's everyone doing? Savannah, Autumn, good to see you here. We got everything going, I think. I'm sending out some last few announcements. We'll get started here in just a second. We're going to start with some harder questions. We'll start from the very beginning. A very good place to start. So we're going to start with chapter Regression and start going over some of the questions. We'll tell people we are reviewing on YouTube. So Autumn, Savannah, how are you doing in the chat right there? I'm gonna send out a reminder, reviewing on YouTube. So reviewing for the test. Great, what about you doing? Good too. Good weekend. We got to see Mark Norman comedy show. Reviewing. Good to see you there, Elizabeth and Ryan. So we'll say click here. We're gonna start with one of the mathier chapters. I'm sending out announcements right now. Reviewing on YouTube, trying to get as many people in here as we can. So, has anyone looked at the sheet I sent out a while ago? Start with that, like how to review. How about that? We'll start how to review. So let me go to the video and then we'll start doing some questions. So we're gonna start questions in a moment. And here it is right here. Let's go to the main screen. Here we go. Okay, really quickly on this then, because I'm probably talking to everyone who's already using the resources, but that's all right if you are not. So how to review? Well, first off, for the test. First off, we've got here the link review to, which will send you to the review page. The review page has a lot of the great information. You can see right there. It's also, I think we have it over here under test review stuff, or it's under the resources and everything, but it's the Stats1 homepage, stats1.utk.edu. And then I created this for our class right here with the walkthrough. If you can email me at bstevens, I can send it to you. I think I posted it to the Discord also, so it should be on the Discord, sent out to my students. I went through and wrote everything. Basically a week-long buffet day, a week-long preparation. Now we've already done the weekend before the test, and we've done the days before, we're on the days before the test. So use this right here, but go to the review page also. And my biggest suggestion, Sarah, good to see you there. A big suggestion I have for you is to print out the practice test. I have full videos going over the full practice test, so we might not do this because I've got full videos doing this. So if you're here now, we can do other things, but if you are wondering how to do any of these videos, you just scroll down right here, and I've got full videos explaining each one, even doing the exam 2 review right here from previous years. I don't think it covers anything. That's the same. No, that's a different song. I gotta watch it. I think that one's been copyright claimed. I think I've got audio going out to different sources. I gotta work on my audio over here. But you can see different problems or different things right here with stratified sampling, where I'm talking about the percentages from the population for each group right there. So check out these videos where I walk through each of these concepts. And it looks like YouTube has auto done the things, voluntary bias, non-response. I think YouTube did it. There's symbols. Wow. Sample, just a sample from there on forward. Okay, with that, let's jump into some questions. What questions or what chapters are people wondering about that people are stuck on while I fix my audio? What chapters? Open volume mixer. What output device? Here we go. Headphones, AirPods. Okay, now it should be doing it. The hardest ones. Print out the formula sheet. I'm gonna see if my things. Can we just talk to students? There we go. I fixed the audio there. Going to the wrong source. Doing interpretations. Let's do some interpretations to start. That is a big one. A lot of people are saying interpretations in the chat. Let's do the 3 interpretations to start. Really good thing. Make sure we have those down. So we're going to mark this in the chat right here. The regression, or chapter 7/8, regression interpretations. So go ahead and then we'll do some probability and sampling. It's a really good chapter. We'll probably do that next here. Go ahead and put the blank interpretations for the slope, the intercept, and the R-squared in the chat. The slope, the intercept, and the R-squared in the chat. Go ahead and put those. You know what I might do? I'm actually going to go into R Studio, and I'm going to do one of my classic ones here and let you see a little bit different, because I think we basically just give you the equation when we're doing it. So here we are over in R Studio. Go ahead and start writing your interpretations. Have it on a sheet of paper in front of you. And I'm going to get some code going here, which you rarely see in 201, but you do see in 320 or 207 and 320 often. So I am making what is called a linear model right here. I'm predicting height from somebody's weight, and we go data equals survey 10. And the graphic over here on the right is known as a what? What is this graphic over here on the right? What is that graphic over there on the right? That graphic over there on the right is a what? What is it? What is that graphic on the right? It is a scatter plot. 100 points, Elizabeth, right there. That is a scatter plot. The scatter plot is a visualization of two quantitative variables. Height and weight are two quantitative variables. Now, think about this. Height and weight being the two quantitative variables. This is the first what for doing regression. So we even have a question right here. So we have a question right here that we can just start listing out. And what is basically, by it being height and weight, we do meet a condition for doing it, which things like GPA and gender would not be, because gender would not be. GPA could, but what are the four conditions for doing regression? Two quantitative variables. Great job, Elizabeth. So two quantitative variables and height and weight meet that because it's two quantitative variables. QQ also, so if you ever hear me call this QQ, it stands for two quantitative variables. Not shape center spread though, because that'll be, there we go, QQ straight enough. No outliers, plot doesn't thicken. QQ straight enough, which means the line goes through the middle of the data. There's a problem here on the high side. Straight enough, no outliers, and plot doesn't thicken. So I'm going to highlight each condition, mention whether or not it's met right here. QQ has to be met to make a scatter plot, and great job, Savannah, right there with the notes in the chat. We're doing that next here. You got it. So QQ means two quantitative variables. It is met because height and weight are two quantitative variables. If you don't have that, you're doing something else. You're not doing regression. Straight enough looks to have a bit of an issue because at the end of the scatter plot, the points dip below. I can also look at this with a choose order and fit the polynomial model. This is something we would do in higher order regression. And if we fit the higher order right here, we can see at the end it has a bend. And look at this. If we allow the line to bend, it would do a better job and it would be a parabola. There's also the lack of fit test we could do, which can be done under check regression to see. So if you'll ever wonder, well, how do we know this? The lack of fit test comes back with an issue with the linearity. These are all things we would talk about in higher level classes to really check. At this point, we're just going to look at the scatter plot and see that the points dip below. So I think it's not straight enough because the line is not going through the middle of the data at all points. It'd be better if the line could bend to go through the data. So I think there's an issue here. So I'm going to put a little sad face right there. So sad face on this one because the line does not go through the middle of the data. We do have QQ. No outliers. Do you think there's outliers here or do you think there's no outliers? Do you think there are outliers like the person who is 75 pounds and 75 inches tall, the person who is 54 inches? I think there are extreme outliers. So this will be super duper sad face. Really bad outliers right there. Plot doesn't thicken. It maybe gets a little thinner towards the edge. What do we use to check plot thickening? How do we check plot thickening? How do we check plot thickening? How do we check plot thickening? Maybe the time order. Sure. Nah, it's not the time order nature of them. We check plot thickening with a residual plot. So I was trying to do it that way, but I can also do it this way. This is the residual plot right here. Notice how it says, I'll put it right next to me rather. How in the world would you know that right there is a residual plot? How would you know if I showed you this from like another class that this plot is the residual plot, the plot of the residuals, which we get in Jump. Jump will give us a plot of the residuals too. How would you know this is a plot of the residuals? How would you know that? How would you know this right here is the residual plot? Like a wild guess. How would you know this plot is the residual plot? Bailey might be saying the answer right there. And I'm going to tell you the exact notes you need to know. How would you know that's the residual plot? I know it's obvious. You just have to be like, oh yeah, of course. How would you know that's the residual? It says it in the title. It says it's a residual plot. And we don't expect you to make these things into a one. We just expect you to know. Here's the thing to know. A residual plot is the best way to check to see if there's plot thickening when it comes to your plot. It's a diagnostic plot of your regression. Remember how I said the line, it dips below at the end, or it should? That's the issue right there I was pointing to, where if we let it bend, it'd be better. Plot thickening, I'd say there's minor plot thickening because the plot gets a little water towards the end. I'd say there's some issue with it. So, and the residual over here, yeah, that's another good one. Great job, Elizabeth. So I would say the plot, it gets thinner, so the model is getting stronger towards the end because the plot's getting a little bit thinner. So the plot doesn't thicken condition. I'm teaching 201 right now, or 207. The plot doesn't thicken condition is checked via residual plot. You want the predictive power of the model to stay the what? You want it to get stronger. You want the predictive power to get weaker. Or you want it to do what? You want it to stay the same. You want the predictive power of the model to stay the same, which means the plot should not get thicker. It should stay about the same. Yep, we're about to do more. These are practice test questions right here, literally verbatim. When I do this voice, remember what's on the screen. The predictive power of the model should stay the same. Put this on the note cards. A lot of people in the chat knowing this right now, that if you encounter a test question that says something like that, you will know the predictive power of the model, which relates to plot thickening, should stay the same. You should also know plot doesn't thicken is checked with a what? The fourth condition, plot doesn't thicken, is checked with a what? Once again, we're doing test questions and we're right about to do interpretations. So plot doesn't thicken is checked with what? Plot doesn't thicken is checked with what? A residual plot. So now let's do those interpretations. So once again, how many interpretations are you going to write out on the test? How many interpretations are you going to write out? How many interpretations are you going to write out? 3 interpretations. The 3 quantities you will write out are the r squared, the slope, and the intercept. Now, you might think that this looks completely different, but I want you to see something right here. Take a look at this output on the screen and also this output here. I'm going to try to put them side by side. Do you see the portion? I gotta scroll down here. There we go. Let me remove things. There we go. Does everyone see where it says parameter estimates and it has an estimate, a standard error, a t-ratio, and a p-value? Does everyone see that? Like, take a look right here. This is the jump output we've seen. I'm going to bring it over here. And it has those values right there. Is that the exact same thing over here on this side? If you take a look right here where it has the estimate, the standard error, the t-value, the p-value. It's the exact same output. So that means this value right here is your value of what? No, well, virtually identical. It's the same. They might have changed a little wording. Good answers right there. This value I'm highlighting right now is your what? And then we're going to interpret it. So we're going to interpret what this is. That value right there is not quite the y. The y-intercept, that is correct. That is the y-intercept. And in notation, that is the value of B0. So if we're taking notes up here up top, we're going to write B sub 0 is going to be 56.3. Let's just call it 56. 0.3. Might say to carry a decimal. What is this value right here now? We'll round it to two decimal places. What is that value there? There are questions on the test that have you look at output. That value right there is what? Well, if you connect the dots, and great job, Sarah, right there, it says estimate of weight, which makes it B1. It's the slope coefficient, not capital B1. It is lowercase b1 right there. So now try to write out the regression equation where we'd have predicted height is equal to what. So this is your y variable, and the equation is in its general format y hat. So predicted is equal to B0 plus B1. Slope, then intercept, always. The way this is written out is like this right here. So I basically put it for you right there. Try writing the regression equation. Great job, Sarah Kate right there has it. Notice we're just plugging in that predicted height because that's what y hat is. Predicted height. It's important you know y hat is that, not y bar, is equal to 56.3 plus, and then we add in the 0.07, and then we add in somebody's weight. So clearly this equation is using weight to predict height. We're using weight Ooh, great job. Oh, Savannah, double check the numbers. You're on the right track, Savannah. That'd probably be 2.5 or 3 points out of 4. Double check the numbers. And then think what you say, because like, no, Savannah, let's throw, and Savannah's just rock starring right here. We got to give points for that, because great job. No, yeah, good work. Like you got this. I want to see you gonna get some great grades. That's why I'm like, yes. So if you notice, Savannah went to interpret the slope right here, and the slope is for each 1 unit increase in X, we expect Y to increase, decrease by B1 on average. So you have to plug in your numbers right here. If you know what 1 unit increase in X is, for each additional pound, does that make sense here? And since we can say pound, I would accept that right there, Savannah. Great job, Elizabeth. And just put, for Elizabeth for that, put height or predicted height equals, you don't want Y equals height, you want to say predicted height. Good to see you there, Narendra. Good to see you there. So you want to say predicted height. For each additional pound, we expect, and there we go, and make sure to say expect or predict, height to increase, because the coefficient is positive, by, and then we put in the B1 right there. Does that make sense? For each additional unit increase in weight, we expect height to increase by 0.07, and then we might even say inches on average right there. And great job, Savannah. And then Savannah, there's a trick to this one. So there is the slope interpretation. So that's our slope B1 interpretation on the screen. And then the next one, there's a trick to it. Does anyone see the trick for the next one? Let's do the intercept, which people are doing in the chat. So the intercept in its blank form is when X is equal to 0, we expect Y to equal B0. Notice how you say 0 twice right there. So with this, we look at what the intercept is. We can see it's this right here, and you can just plug that in to the value of B0, because that is the value of B0 there. And now we put in the X and the Y when X is equal to, which is X is going to be weight, is equal to 0. We expect height to be 56.3 inches. But what about this? Talk to me about it. So now I need you to do a little bit more, because we always say comment if illogical. And then, yep. And then you'd want to write one additional sentence to say, this doesn't make sense because if you weigh nothing, you don't exist. Does that make sense? Weight can't be 0. You can't be 56.3 inches when you don't weigh anything. Bailey, that would be 100 points right there. Perfect answer. This is what you would add to it when you comment if it's illogical. It just doesn't make sense. This doesn't make sense because if you weigh nothing, you don't exist. Sometimes intercepts can be illogical. And great job, Savannah, right there. And perfect. And we do want to say this for R squared. One of the biggest things we always repeat about R squared before interpreting it is that it is not what? R squared is not what? Savannah already grabbed the R squared. Oh, wait, Savannah, you might have a different number. That's the B0, Savannah. That's not the R squared. R squared is not what, though? That'd probably be 3 or 3.5, Savannah. You just grabbed the wrong number. R squared is not correlation, which is correlation. Do not interpret it like correlation. And then some people try for some really, I swear they might be chat GPTing it or something. I don't know. But they give some answers that are very people would have a hard time understanding. It's very mathy, like our reduction in the variance from the naive model. And it's like, no, we're going for the business interpretation right here. We want you to interpret it so people understand it, like how much it gets us to understanding. I wouldn't use this, but we also technically in upper level classes accept things like knowing somebody's weight gets you this % of the way to understanding the variation in their something. So if you were doing jump output, R squared is located right here. Does everyone see where R squared is at? So for this model, R squared would be 27.4. So we would just say it's illogical and then explain exactly like you can't weigh nothing and have a height. So that's where R squared is at in jump output. It literally says R squared. So let me ask you this. If we give you jump output, will it be easy to see what R squared is? No, that's for that one, yeah. So if we give you jump output, yes or no, will it be really easy to see what R squared is? Yes. Now, we'll talk in a moment about how to get r from this, but let's interpret it. R squared for this output, I won't make you find it. It's right here. It's the multiple r squared. So that is the r squared for this output. So r squared is blank percent. Make sure to times it by 100. So multiply by 100 of the variation in y is explained by the variation in x. So go ahead and just try writing it out. People are already doing it in the chat, getting good practice. Remember, if you're here writing it out, you're just getting practice. So go ahead, try writing it out. I'm going to write it out here in 1 second. I can get started because we got a lot to do today. So give it a try writing it out. It's literally just plugging in the values, and we're predicting height. So you can basically see it right here, and then you take the r squared, multiply by 100. So it just moves the decimal around, and there you go right there. 36.13% of the variation in height is explained by the variation in weight. It is not correlation. Yeah, and that was another model, Savannah. So as long as you grab the right one, you're fine. But Savannah, great answers right there. That's what you would do. Just grab the right r squared, and it'll be very obvious. This was a different model from JUMP, but it'll be very obvious what the r squared is. It'll just say it right there. Like if it was in JUMP output, it'd be right there. So you got the right answer. With that, here's the thing though. If we go from r squared to r, what are the two steps? If we go from r squared to r, what are the two steps? Another question here, switching topics. If we go from r squared to r, what are the two steps? Really? Wow. I can find it. Square root and look at direction. I was trying to find a negative. So I was looking very hard for a negative. I don't know if this is a negative one. Analyze. No, that's so Pokemon. Analyze. Fit y by x. Let's look at defense. Is it all positive correlations? Here we go, finally. Finally. Wow, it's 0. That's totally random. Weird. Okay, I can't find a negative correlation today, apparently. Last try for a negative correlation. Here we go. Negative correlation, anybody? I don't want to do that many. Oh, this should do it. Square root and look at direction. Perfect answers. Finally, what is the correlation for this graphic? What is the correlation between average wind speed and demand? So take a second right here. See if you can find the correlation between average wind speed and demand. So I think going backwards, the squared. So, okay, I think I've about got it. See if you can find it. What is the correlation between average wind speed and demand? What would it be? What would be the correlation between these two variables? So basically you have the steps in the chat right now. So what is the correlation between those two variables up there? We're just applying what we have in the chat right now. You're just taking what it says in the chat where it says square root it and look at the direction. That's r squared and we want r. You're just taking your knowledge and what you've said to do. So what is the correlation between those two variables over there? These two right here. You got it. You can do it. Throw some points. That sounds about right. Yeah, that sounds about right. Oh, but Savannah, take a look though. Even I blinked for a moment. Wait, Savannah though, and then Sarah Kate has it, I think. Sarah Kate has it right there. Take a look what Sarah Kate has. Remember, so we're saying it in the chat is that you square root this. Remember, so you square root it, and then you need to look at the direction. So there's the answer right there. Does that make sense? Are people seeing it? That is the correlation between those two because it's negative. So it's negative 0.2368. And that's the linear strength between them. It's a weak negative correlation. That's not the slope. That is the value of R. So this is not B1. That's not a slope coefficient. The slope of these two variables is down here somewhere. The slope is negative 82, and the correlation is negative 0.23689. So make sure to take this and square root it right there. That is the key. Does everyone see that? Square root and check direction. It is significant because it's lower than 0.5. Yes! And I think Savannah's pointing out right there that, and this is the last thing, we've covered a lot of this chapter now, is that the slope is statistically significant because the p-value is below 0.05. So that is a statistically significant slope right there. Like this p-value right there, the one I'm touching right there, is the significance of the slope, which is the significance of the model. Because it's below 0.05, the slope is statistically significant. One more question right here, then we're going to switch topics. If a residual is positive, let me put this as a question in the chat. Don't answer it too quickly, or don't say it out loud. If a residual is positive, what was larger? Don't answer. So if a residual is positive, what was larger? And so here it is for you. And I'm going to go to the equation of a residual. Check out last office hours where I went through the full formula sheet. And so if a residual is positive, what was larger? And you have to know the formula sheet a little bit. It makes it really easy to answer this. And we go to the formula sheet right here. And on the formula sheet, you see that a residual is equal to what? What does that say for a residual? It says a residual is a what? The what? The residual is what? What is a residual? Actual minus predicted. Great job, Bailey, right there. That's the way I usually abbreviate it. Residual equals actual minus predicted. So think about this. If you plug in numbers like Bailey has right here, if we plug in 8 equals 70 minus 62, if you look at the positions right there, if the residual is positive, the actual would be bigger. So great job. A lot of people in the chat getting actual is the answer. If it's positive, the actual would be bigger. And so right here, you can see this has a positive residual because it's where? That has a positive residual because it's where? Explain to me why this point right here has a positive residual. Because that's its actual. That's what its actual Y value is. Its actual Y value is over here at like 9,000. It's above the line. That's all I was looking for. Yeah, exactly. It's above the line, and the line is the predictions. So its predicted value would be where the line hits the Y, and its actual value, so its residual is this distance, how far it is above the line. Good morning, Reese. Good to see you there. It's above the line at best fit, which the line makes the predictions. So that's where the Y hat comes from. This is the equation B0 plus B1x. So it's above the line, and anything on the line would have a residual of 0. 2 more questions, then we'll end this. Summing up all the residuals will always sum up to what? Summing up all the residuals will always sum up to what? So I'm going to go right here and say round to 2 decimals, the sum of the residuals. So the round to 2 decimals, the sum of the residuals, and it should go to 0. So it's because the line is through the middle of the data and the data kind of sandwiches in around. So I can prove it to you mathematically that summing up all the residuals. Now you say, why did you round this, Brian? It's because of literal tiny decimals make it look like there is something, or if I do the sum of them. But summing up all the residuals goes to 0. That's a very, very tiny number, just fractions that are not getting carried over properly, even for a computer, but it's 0. Predicted power of the model should what? I hope no one misses this because I've said it like 50 times and it's not like I know it's on the test or something. Predicted power of the model should what? You'd think stronger, but that means the plot is thickening or getting thinner. Predicted power of the model should what? And then we're switching over to, let's switch over to chapter 12. Stay the same. It should stay the same. The plot shouldn't thicken. Okay, great job right there. Reese knows too. Let's switch to some chapter 12 probability. Okay. Probability was a weak point for us. So we're doing chapter 12 probability. Shout out what you want to do. We'll probably do it next. Okay, so I'm going to come up with 3 probability questions. I want you to try to start to solve them here. We go to a casino where we know from playing blackjack that, let's see, I'm just gonna find out. What are the odds of getting dealt blackjack in blackjack?
The chance of getting a blackjack.
48. Or we'll say 5%, it'll make life easy. Here's your questions to start for probability. There you go. So write out the sample space to start, or even define what a sample space is, then write it out. So I want you to know what a sample space is. And if you get a question like this on your paper, you need to write a sample space. These are the steps, if you've watched me solve these problems, to do them correctly each time is to write them down. So start by writing your sample space. You can do it in the chat now if you want to practice, and I'll start checking answers. I'm going to write about 5 or 6 questions, and we're going to start solving all of them, and they're going to go from like easier to more difficult. So try solving these. It's a list of all possible outcomes. Exactly, it's not the sample frame, the people we have access to sample. It's sample space is every possible thing that could occur. So that is the chance of a blackjack right there. There you go, blackjack. And basically, keep going, and write out the sample space. What is the sample space? All possible outcomes with what I've written. I'm only asking for what I've given you, blackjack, and then, you know. I think people are doing a great job. Reese right there. Probability of a pair. I want to be accurate. What is the probability of a pair in poker?
It can be formed 4 ways, one for each suit, giving it a probability of 0.0000154%.
You'd have 3 cards that match. There's always 3 cards that match. So it's 3 out of 51. So 3 out of 51. So it's basically 6%. This is the probability you get. I'll do this then. Let's be accurate. Okay, these are good. Keep answering questions. I'm writing probably a few more. A good theory question. Reese is on the right track. All right. Okay, so this is a lot of the chapter right here. There we go. And so Elizabeth right there is already giving the sample space. With what I've listed right here, I wanted a rather simple sample space to start, where the sample space is going to be, and this is how to write it out. Great job, Reese, right there. I think, and we'll check some answers here, because I wrote some trick ones on there. So the sample space, when you write it out, you usually write the event, the probability of the event. So we've got here blackjack and not blackjack. Does that make sense for everybody? We got blackjack and not blackjack. So either you're going to get delta blackjack or you're not. And the probabilities are associated right here with them. The sample space must add up to what? Which is the second rule of probability. If you have a valid sample space, all probabilities are contained between 0 and 1, and the sum of the sample space is equal to what? The sum of the sample space is equal to 1. So a valid sample space will add up to 1. Would the sample frame be not so sample frame is Reese, good questions right there. Kind of, sort of. Yeah, I guess it would be. I got three's 500 points. Be very careful because I guess it would be, Reese. The sample frame is going to be everything possible we could sample. We don't really use it in this chapter. It's used more like you stand outside the library and talk to students. Your sample frame are students who walk by the library. The sample space is all possible combinations of outcomes when it comes to probability. So the sample space has probabilities associated with it, or the sample frame. Yeah, and so sample frame, think of like a tray that looks like a frame and you're picking things off the tray that you want to try. And so you're sampling things like a dessert platter, I think about. And if you think about the dessert platter and it has different desserts on it and you can only eat like 5 desserts, you're going to sample different desserts on here and try them. That's a sample frame, but a sample space, I guess, it can be confusing. I'd put them on cards. Sample space is the list of all possible outcomes with associated probabilities. The sample space of the two things are what? So because either you get a blackjack or you don't get a blackjack. So these are obviously what's of each other. You either get a blackjack or you don't get a blackjack. They are what's. Looking for one word right here. I'm trying to cover a lot of the rules on this chapter. They're complements. They are complements because they add to 1. So a complement would be everything that could occur versus everything that would not occur. Either you're going to get a blackjack or you won't get a blackjack. The best way to do complements is either this occurs or this does not occur. Like, I'm either going to get to work in 15 minutes or it's going to take 15 or less minutes, or going to take me more than 15 minutes. You say, well, if you don't get to work, well, then I didn't get to work in 15 minutes. It took me more than 15 minutes. I never got to work, you could say. So, but the complement is either this occurs or doesn't occur. You'll either take this long or you won't take this long. Sample space is all possible outcomes. The best definition of it is all possible outcomes. Like a dice has a sample space of 1. It's kind of results. It's just outcomes of things. Like one of those outcomes must occur when you roll a dice. That's the sample space of rolling a 6-sided dice. All the probabilities are equal. They don't have to be, but a dice would have an equal sample space of 1, 2, 3, 4, 5, 6. What is the probability of getting 2 blackjacks in a row? I think Reese already did it. Now, a lot of times, and let's just say this, let's say it's online poker or something or online blackjack, where they're shuffling the cards between each thing. So if the cards are shuffled, and this is a key assumption, and Reese has it right there, assume cards are shuffled between each play. Why would you need to assume the cards are shuffled? Because this actually gets into card counting now. Why would you need to assume the cards are shuffled between each play? This means we've done what right here? It's kind of, random is correct. Random is correct because if it's random, it'll be what of each other. If it's random, each hand, like getting a blackjack, would be what of getting a blackjack next time. So if you assume the cards have been shuffled, independent, right there, independent, and Savannah and Reese right there. So that's why if it randomizes the cards, then each hand is independent of a previous hand. And do remember, I can't state this enough, are the answers to the conditions on your formula sheet. I know I'm just asking you to type yes right now, but I want you to see this. Is the condition here for multiplication right there? It's right there. That it says to multiply two things, they have to be independent. And that's what I'm stating by saying the cards are shuffled between each one. So the answer is simply 0.05 times 0.05. Read as I got a blackjack and then got a blackjack. And then I got a blackjack. You bought it, I thought I'd post in like spam or something. But this is the multiplication right there. That is the multiplication rule, to use it right there. If the probability of getting a pair is 6%, what is the probability you get a pair or a blackjack? Now, before doing this, what should we check? So before doing this, what should we check? And if you don't understand blackjack, I'll explain the things you maybe need to know. What is the probability you get a pair or a blackjack? Remember, we're remembering to look at our formula sheet anytime we ask things like, well, wait, it's a pair or a blackjack. A pair or, and Savannah's starting to see it right there. And Savannah, that is correct with that change. And then what do we need to check? And if you don't know blackjack, I'll explain. Like, if you know what to check is more important here. We don't usually use things that you'd have to have knowledge of to check. No worries, Savannah. What do you have to check for this? What just says right here. Yeah, no, I wouldn't use this as a test question. Are they mutually exclusive? So you have to ask me, can you get a pair and also a blackjack at the same time? A blackjack is when you get 10, jack, queen, king, and ace, and they are disjoint because if you have a pair, you have like ace, ace, 10, 10, which none of those are a blackjack. So if you get a pair, you can't get a blackjack. If you get a blackjack, you can't get a pair. It's like if it's 100 degrees outside, it can't be snowing. If it's snowing, it can't be 100 degrees. Disjoint means if one happens, the other can't, which is the same word as mutually exclusive. So for those who don't know blackjack, which is not the point of this question, if you get a pair, you cannot have a blackjack, confirming they are disjoint. So the answer to this question is what? So these are disjoint. Yeah, I love it. Nice. So they can be added. So since they are disjoint, we just take the probabilities associated with this, and we get the following, that it's a probability of 11%, that in your hand you'll have a pair or a blackjack. What is the probability? If the probability of two different cards is 94%, what is the probability of two different cards or a blackjack? Now be careful right here. What is this? I like this now. Well, be careful though. What is a hand that's a blackjack? What hand would be a blackjack? So what hand is a blackjack? If you know that, and I'll try to do it quickly because there, Reese is, yes, Reese, this is where the problem is at. Reese is getting into it now. So Reese is pointing out some issues right here. So here's the issue, Reese. Blackjack is the following. One of these can be a blackjack right here. Here's Jack, Ace. That's a blackjack. Does that make sense? That's 21 blackjack. What do you notice about the blackjack right here? What do you notice about this? And I want to point out the key words again. I should have been circling these. Is the or right there. I want to go back up and highlight these. And this is the and right here. What do you notice? Yeah, no worries, Autumn. This is good practice. The blackjack is two different cards. Does everyone see that? Can you get two different cards and can you also have a blackjack? And the blackjack is two different cards. Reese is starting to see it now. It is not disjoint because you can have a blackjack and have two different cards at the same time, which means we cannot what these. This is a trick question I wrote right here. There is a way to solve it with more advanced probability, but you cannot what these because why? So repeat, because this is what we got to check right here. You cannot add them easily because they are not disjoint. So make sure to have your formula sheet beside you, and whenever you hear this or this, you see how it says or right here? Whenever you hear this or this, remember, and that's why I was circling the or. It always helps to see it right there, not that one. There's the and right there. But when you see or, it's going to be addition. And since these are not disjoint, we can't easily add them. So we'd say not disjoint. We'd just say not disjoint, can't solve this problem. You need to teach me more probability, Brian. These are not disjoint, don't add. Don't just simply add them. There's a way to do it. We would not just simply add these. My pen is having problems running out of ink. What is the probability you have an amazing time in Vegas and hit multiple blackjacks at the table? Now, I wrote this one very vaguely for a reason. Now, we already did one trick question. You will know for sure on the test. Yep, it's it. Savannah, we make them pretty clear on the test. Always check, though. Yep. Yep, exactly, Reese. So this one says, was probably have an amazing time in Vegas and hit multiple blackjacks. Now, what word do you notice first? This is a trick question. I'll tell you that much first off. What does it want you to probably do here? So it's like, what is the probability of this right here, amazing time in Vegas, which is probability amazing time. And then it wants and the probability of multiple blackjacks. So probability multiple blackjacks. So, well, but are they disjoint? But what should we be checking for this? This is where always have your formula sheet next to, if you write it out, what should you be checking for this? What should you be checking for this? I know, this is the key word, right? What is the probability of this and this, right? So what do we need to check? So we're practicing how to do the test. Well, Sarah, you are correct, but what should we be checking right here? It is a trick question on purpose. We don't gotta worry. We could check disjoint, but since we're doing and, does everyone see the steps right here? I'm trying to make sure we know the steps. Do you notice how right here, we are gonna check to see if they are independent, because the question says, what's the probability of this and this? If it says, what's the probability of this or this? So repeat with me real quick. This or this, check to see if they are what? This or this, check to see if they are what? This or this, check to see if they are what? This, correct. This or this, check to see if they are disjoint. This and this, check to see if they are what? Remember, look at your formula sheet. This and this, check to see if they are what? This and this, check to see if they are independent. We're just looking at the formula sheet, following the formula sheet. So the wording of the question is, what's the probability of you having an amazing time in Vegas and hitting multiple blackjacks? So let's see if they're independent. If I hit multiple blackjacks in Vegas, do you think that would influence me to have a better time in Vegas? If I hit multiple blackjacks, and this is what independent means, it should have no influence if they're independent. Like having a great time in Vegas, I think it would influence you. So these are very clearly what? Finish my sentence. These are super duper clearly what of each other. Use the right wording though, because we're checking and. These are very, very clearly what? Very, very, very clearly what? Very, very clearly what? Dependent, not independent. But they're dependent because how good of a time you have in Vegas would depend if you hit blackjacks. I'm not saying you can't have a good time without hitting blackjacks, but if you hit a bunch of blackjacks, you're probably gonna have a better time in Vegas. So they're super duper dependent. This was only just a trick question. I think someone got it right. There was no probabilities with this. I think Sarah said it. It was just to check the rule here of independent. Does that make sense what we were doing? The whole point of this was to make sure when we see and, we know that this is multiplying and we need to check if they're independent of each other. So if they are dependent, can we do anything with it? There are mathematics ways to do it. So let me write here, equation for multiplying two dependent probabilities. Here it is right here. There is a way. So it's the probability of A and B is the probability of B times the probability of A given B, which equals the probability of A times the probability of B given A. So you have to figure out the probability given B occurs. Like you can solve each of these. But notice how you're not just doing the probability of A times B. When they're independent, the probability of A and B is simply the probability. Does that make sense? So this is the complex equation right here. And the multiplication rule is only for two independent events. When they're dependent, then the probability is listed below, and we don't do that here in 201. But think about this. If the probability of A doesn't depend on B, then it would change. Exactly, not step to one material, exactly. So this means probability of A given B, but if B doesn't change the probability of A, then it would be the same. Probability of A given B would be the probability of A. So for those who want to know the mathy, nerdy stuff, it'd be equal to this when independent. Oh, there it is. Well, they might be listing it out. But that's the more mathier, nerdier stuff. We just multiply together and we check to see if they're independent, easily multiply. What is the probability of 10 non-blackjacks? Probability of blackjack is equal to 5%. What is the probability of 10 non-blackjacks? What is the probability of 10 non-blackjacks? Reese got it right there. It's not getting a blackjack, not getting a blackjack, and not getting a blackjack. Assume they shuffle cards between each hand. Assume cards are shuffled for independence. So that's an assumption. We'd have to assume that. And then Reese is probably doing the next one. Was it equal to basically 0.6? I like that. 0.95, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there it is right there. Basically 0.60%. Man, so you could play 10 hands. It's likely you wouldn't get a single blackjack. It's more likely. What is the probability of at least one blackjack? So you have to write your sentence right here. So you're either going to get at least one blackjack or what? You're either going to get at least one blackjack or what? You're either going to get at least one blackjack or what? At least one or what? You're either going to get at least one blackjack or what? You're either going to have at least one blackjack or what? Or no blackjacks. And since one of these must occur, it equals 1 because you're either going to get at least one blackjack or you're going to get no blackjacks. Now we want to find in 10 hands, remember it's 10 hands, we want to find at least one blackjack. So we're just going to algebra this over to the other side. And does anyone see the math? And I set us up for success. So what is this going to be? I can tell you the answer because I can see some of it already. Round it to 1 decimal. What is this going to be? What's the probability of at least one blackjack? You can do all these, really good work. Yep, that's right. Because we just figured out this right here. That was from the previous problem. So in the previous problem, we figured out the probability of no blackjacks, which is this right here. And then at least one blackjack, either you get no blackjacks or you get at least one. And it is that, right? It's 0.40. The probability of none is 60%. The probability of at least one, because either you'll have no blackjacks, which we already found in 10 hands, or you'll have at least one. So this was the probability of no blackjacks, which was the probability of 10 no blackjack hands in a row. So in 10 hands, the probability of no blackjacks is 60%, found here mathematically. Then just carry this down because either you'll have no blackjacks or you'll have at least one blackjack because those are complements. Any questions on this last one right here? Really good, tough question. This is covering a lot of the chapter. This is, if you could do all these problems really quick, you probably understand the problem pretty well. I'll do one more advanced one. I think it relates to the test, hence why I want to do it. Let's do a question 9. Your favorites. You're welcome. We'll do some more questions right here. Your favorite. Yeah, good. I like hearing that. Candy has a contest on it. You know that 30% are winners. You and your friend buy a candy. What is the probability? This is a more tough one, more difficult problem right here. We'll go to a new page. So, what is the probability that one of you wins? This is kind of like the car one. So if you're wondering, well, why in the world can we give you a question like this on the test? It's very much like the My Pearson car one, where you have a car with repairs. So first thing you're going to do when you're solving this out is write the sample space and then find probabilities. So what is the sample space right here? Maybe that's probability the candy's a winner. I think Savannah's going without it. Let's write the sample space. So the sample space for one candy, which we're going to go a little more complex here in a second, is going to be the event and the probability of the event. And the event is either going to be win or lose, which is not win. And but Reese, here's the thing though. That's not the full thing. What's the Reese? Keep going on that, because the sample space is not no one wins, one person wins. There's also what? Remember, there's only two right here. So Reese, you're on the right track, but it's not no one wins, one person wins. You'll actually see it right here. You're basically there. So you're really close, Reese, with this. One wins or both wins. So what you can actually do is you can do the probabilities or find sample space for two people. So the sample space for two people, show me the sample space for two people. What is the sample space, like event? Write the events first, then we'll write the probabilities of the events. So tell me the sample space for two people. What is the sample space for two people trying to win? What is the sample space for two people? Yep. And so now you have to be careful though. Well, basically write it out in terms of like this right here, Reese. Write it out like that. Continue filling in the sample space. I've done this like once or twice in class. Not quite. Not quite. When you see it, you'll be like, okay. But keep writing it like this though. Keep writing with this sort of lingo I got on the screen right here. Because then it'll make more sense when you see it, I think. You get practice at doing it. What would be the remainder of this? I've only got a few more to do. LL, and then what else? And then one more we're missing. So we have you both win, you win, they lose, and you lose, they win. And guess what we can do? We can start putting the probabilities right here. See if you can start solving it. There's multiple ways to solve it now. There's multiple ways to solve it now. There's a lot of ways. With this info on the screen, there's a lot of ways to get the right answer. So I know the answer right now. See if you can solve it. There's a lot of ways to get it. What is it going to be? We want to see the probability that one of you wins. Not at least one of you wins, one of you wins. If you can get it, I'll say the answer in a moment. Probability one of you wins. Probability one of you wins. Well, which of these are one of you winning? Which of these is one of you winning? Like, can you write out which of these is one? Reese got the answer. Reese got the answer. No, the first one, Reese. Because it's either this or this occurs. So when we say this or this occurs, what are we doing? Great job, Bailey, right there. When we say this or this occurs, what are we doing to those probabilities? When we say this or this occurs, what are we doing to those probabilities? Well, don't add all three of them. We would just add the two of those. Does that make sense? We'd add the two of those. Because either you win and they lose, or you lose and they win. And we also have, so this is the addition rule right here, and this is the multiplication rule right here, multiplying. So the answer is point, here we'll write it in black right here. This is a good, tough question. I said we'll write it in black. There we go right there. Oh no. And Savannah, really good practice here. Thank you, Savannah, and everybody for being here practicing. Really good stuff. Really good practice. Yeah, I'm trying to give the hardest I can give. So we're going up to the highest level right here. Like, I don't want you to be shocked by any test question. Once again, remember, write out your sample spaces. I'm going to the highest level on the difficulty of questions that I believe are on the test. I can't promise you I've shown you everything. I mean, I'm trying to. We've covered every concept, but then I try to replicate questions with asking something like this right here, and then notice the steps. And I can't state this enough. Rewatch this video and just try doing the steps. Try writing out the sample space. Sample space lets you visualize what's going on. Like Reese and Savannah, does it make more sense when you see it right here when I say either you win and they lose, or you lose and they win? So now I win and they lose, or I lose and they win. Yeah, when you see it right there and you read it off as an equation, like one of those things must occur, like either I win and they lose, or I lose and they win. And then you can see right here, either I win and they lose, or I win and they lose. So seeing it, writing it down really helps. Reading it as a sentence helps. Try saying it out loud. Try doing what I do. There we go. Okay, we haven't covered chapter 10. Chapter 10 is a big thing on notation. All the sample space stuff just confuses me. Yeah, I know, right? It's very mathy. Hence why I probably like it. Let's do the sample space. Chapter 10, sample space. Okay, or not sample space. Sample surveys. Chapter 10, sample survey. Okay, start listing off terms for this chapter, as in sampling methods. So sampling methods, overview, or sampling ideas, like, or sampling terms, general sampling terms. Biases, stratified. Stratified is, there we go, cluster. Oh my gosh. Cluster and simple random. We'll put them in order. Usually these are towards the end. Simple random and systematic. And there we go right there. Multi-stage, 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 multi-step. Same sort of thing. I don't like the multi-stage questions when we give them. Make arguments and stuff. General sampling terms right here are going to be what else? So then people are already listing other ones. The biases are things like non-response, response. It's generally called undercoverage, but same sort of thing. It's good answers there. Autumn, same sort of idea. Undercoverage, overcoverage. And voluntary inconvenience. Sometimes I don't even, what else do we have? Did I miss anything? Up here at the top, we have sample, statistic. See if you can write these down with me. Like if you know them all. There we go. Sample frame, sample space is a term used more in chapter 12 for all possible outcomes that can occur. So when we start going here to the definitions, we have that a sample is going to be the individuals. We'll do a normal thing. The individuals we collect data on. The individuals are things we collect data on. Associated with n equals something like 200. We sampled 200 UT students. Always try to think of an example right here. Yep. So always try to think of the notation and an example. A statistic is a summary of information collected from a sample, because statistics give samples give statistics. For example, y bar. We'll insert it. We'll just do yeah, y bar. Y bar is the sample mean, which would be something like, from the 200 and students, we found a mean GPA of 3.4, which is y bar. Does that make sense right there? That is a y bar, which is a sample mean, which comes from a sample size. Population all people or things we want to understand. This would be like all UTK students, which would be n equals to 35. Capital N, notice capital N. The true information we want to understand about population. Sometimes called parameter of interest. This would be like the true GPA of all 3,500 students is 3.5. So what is this in notation? I'm gonna have to go find it right here. But what is the true GPA in notation, which is a parameter? Like this value, the true GPA is a parameter, and it's known as what? Not P. Good guess. That is the true proportion. The true mean is mu. The true mean is mu. So the true proportion is P. The estimate of the true proportion is P hat. So we would have right here, we could also find from the sample the proportion who go to Taco Bell. This would be P hat equals something like 40%. No worries. And then mu, well, mu is not Y hat. Y hat, so just to clarify, Y hat is the predicted from the regression equation. Y hat stands for predicted Y. Y hat is the value predicted from the line. That is what Y hat is. Mu is the true mean, stated like the true GPA of UT students is 3.5 for all students. Does that make sense what that is? P hat is the estimate from a sample of the proportion. If somehow we did a census, collected all the data, and knew 42% go to Taco Bell, we'd know P is 0.42. Does that make sense? So if we knew 42% go to Taco Bell, well, Reese, good answers. You're thinking, you might be thinking mu P hat equals P. I know there's a lot of crazy interesting information right here. You might be thinking mu P hat equals P, but this is not saying mu equals P or mu times P hat. How do we read the mu right here going into chapter 13? How do we read the mu right there? That's read as the what sample proportion. Yeah, no worries. This is why we're covering it all. That's not the true mean sample proportion. It's often read as what when we think about it as a sentence. Think of an E word right here. And check out the previous chapters. I think we did a big review last week too. Well, mu P hat is P. That is correct. And then how do we read mu? The mean of the sample proportion, basically, Savannah said it expected. We call this the expected right there. I expect a sample proportion that is the true proportion. I expect a sample mean that is the true mean. This is a tougher chapter, chapter 13, so we'll take a look at this here soon too. But this is the true mean, and this is the mean of the sample mean, often read, I expect the sample mean to be the true mean. Check out those chapters, and we'll probably do that next year. The sample frame is going to be all individuals we have access to sample. I go outside Hodges and talk to 200 students. The students who walk by are my sample frame. The 200 students are my what? So the students who walk by me, who I could speak to, are the sample frame. So the 200 students are my what? I talk to 200 students. The 200 students who I talk to are my what? The ones I talk to and get information from are my what? What? The 200, they're my sample. Great job, Deep, right there. They are the sample. For 100 points. They are the sample right there, the 200 students I talk to. But the ones who walk by, I could theoretically talk to. Like maybe I'm busy talking to someone, but someone was in my sample frame because I could talk to them. Does everyone understand what a sample frame is? The sample frame is more theoretical. It's not who you spoke to. It's It's not who you want to understand. It's who could you theoretically have talked to. Kind of, sort of. Once again, another chapter topic used in chapter 12 for probability. It could be done for this chapter. The sample space would not quite apply to how we're speaking here right now, because the sample space refers to all possible outcomes. Technically, the sample space of who you could sample would be every combination of everyone in your sample space. So this is where it gets crazy, Reese. Check this out. If you want to think about the sample space, you'd actually be looking at this. So not choose order. We'd do choose. If we were to choose from 500 students 200, that's what your sample space is. Like, this is the sample space of combinations of students you could pick. If you say I have to sample 200 students with 500 walking by, that's how many ways. I mean, it's like, what is this? Is it Google? I don't know. That's like more than a quintillion. It's like a billion times a billion. It's probably bigger than a billion. It's way bigger than a billion times a billion. What am I saying? That's like a billion times a billion times a billion times a billion. Might be about right. It's a ridiculously large number. So basically, your sample space is kind of immeasurable. There's like so many different ways. So that's why when people get the same random sample when we do the projects, I say it's impossible virtually. You're welcome, Bailey. Good stuff right there. That's a lot, I know, right? So basically, don't get the same random sample as someone else. It doesn't happen by mistake. It doesn't. I mean, it could. It's like winning the lottery like 5 times in a row, or I calculated it. It's ridiculous. And that's, yeah. Anyways, sampling methods right here. Simple random sample. A key thing and a way to remember this is, how do we remember simple random sample? Everything is given a number. Everything has an equal chance of being selected. It's literally like going to the registrar, and they select random student IDs. And it's pretty simple. It's pretty, you just give everything a number. It's like putting everything in a hat and drawing it out. So simple random sample, everything's given a number. You draw the numbers at random. That's simple random sample. Systematic, what is the key thing you always look for in systematic? I hope no one gets this wrong, because it's going to be there when you're doing systematic. Technically, no blackjacks. You can technically start at a random point. Not required, but is good. Well, kind of. There's a key component to it where we talk about, you should notice this, kth observation. Autumn got it right there. And select every kth observation. Like every first, or don't do first. Every 5th, every 10th, every 15th. So every nth. Great job, Deep, right there. Really good comments. So second, yeah, because you got to do that. Great, Deep, Scott. Let's start Deep, 500 points. Really good comments right there. Every kth observation is a good way of saying it, or every end, second, third. But usually we space it out a little bit more. That depends on what they're sampling from. Just depends. You got to figure out how it works for you. Stratified, put it here, step. Step 1 is to first acknowledge a difference. Step 2, sample with respect to that difference. So when you think about this, it's something like, we want to sample UT students, so we take 500 undergraduate and 50 graduate students to ask them their views on parking. Why did we take so many more undergraduate students? It actually gets down into the bottom thing, because we often stratify to make sure we do it respective to certain groups. Why did we get 500 undergraduates? Theoretically. Good to see you there, Kyle. Bring back long hair. That's super short hair, Brian. Why did we take 500 undergraduates? We have more undergraduates, so you want to do it representatively. So if you notice when I say, like, acknowledge a difference, grads and undergrads probably have differing views, and then sample with respect to that difference, like, do it respectively, that you take the proper proportions. And so stratifying is layers. That's what strata means. And you're acknowledging the differences to say, well, maybe the graduates have a different feel about parking than the undergrads. So let's make sure we get the good, like a proportional amount of graduates. and you'd have to know the proportion in the population. Like, you'd have to understand that. Reese, great job right there. You're welcome. Cluster sampling right here. The steps for clustering sampling are: step 1, things are randomly put into clusters, ideally random. Sometimes not so random, but ideally. Step 2, select clusters at random. Step 3, perform a blank on the cluster. Perform a what on the cluster now? Looking for a C word right here. I'll start writing an example. We go out to classes at UT and select 10 classes at random and speak to, great job, to all students in the classes regarding their views on parking. Now, classes aren't random because where you go in the ag campus, main campus, HSS, Haslam, but if we were to assume they're random enough, we might say that they're decent clusters. Notice how things are put into clusters, groups, and then we select different classes, which those are the groups right there, and then we perform a census. So you'll always see this word like all right there. Multi-stage, there's about 1 billion examples. It's hard to, it's like where you combine them. Go to every 5th table in the dining hall and speak to all students at the table. So this would be an example of what right here. Go to every 5th table in the dining hall and speak to all students at the table. This would be an example of what? Oh, it already did it. Go to every 5th table and speak to all students at the table. It's a multi-stage because you're doing like every kth observation and systematic and then systematic cluster. Yep. So it's just pairing it together. It's just taking Legos and putting them together when you do multi-stage. So multi-stage is just using multiple methods. Make sure to look through these right here and to understand them as we write them out. Make sure to write these down too. A lot of people say, can you send me it? And I'm like, it's better if you write it down. Like, you want to write it down, you want to say it, you want to practice it. We go to the biases right here, non-response. People who don't respond have differing opinions than those who do. So an example of this, classic one, is you call people on the phone and they don't answer your survey. So maybe they're leery of people who do phone surveys. So problem right there. Do you have the timestamps? Yes, we are. Yep. Thank you so much. That's what I always add to the videos. So you can come back. We've been timestamping this right here. Thank you. Let me go ahead and hit save right there, Kyle, so I don't mess up, because sometimes I forget to hit save and then I have to go back and do it myself. Response bias is going to be the actions of the surveyor. You're welcome, Kyle. Or people just lie, influence people. So it's like response bias is when you're not getting someone's true response. When you ask questions like, how much money do you make? People usually are like, I don't know, how much money do I make? I mean, I just did my W-2, but I don't know, 40,000, 50, 60, I don't know. So you get very interesting answers. And I hate that usually people put it into brackets when they talk about how much money you make. Like, I just want a quantitative number. I can discretize it afterwards. We call that discretization of quantitative data to put into discrete groups, but you don't get as much information from that. But sometimes we use brackets because people are like, well, it's kind of nebulous. You won't know exactly how much I make, but I'm doing a survey. I just want to know the real answer. But due to response bias of the way the question's worded, the actions of the person given the survey, we don't get true responses. So I think what response bias is when you're not getting the real response. Non-response is when people don't respond. Under coverage is leaving out a group in your survey. You can have too much of a group. So over coverage causes under coverage if you have too much of a group. Like, I go out and I only talk to Republicans about who they're going to vote for, or only talk to Democrats. I've over covered the one group and I don't have enough of the other, or independents. But you want to make sure you have proper representation, a representative survey. That way you do not have this kind of bias where you've undercovered. Voluntary bias, when people who volunteer have stronger opinions than those who don't, such as sports questions. Anytime you're doing sports, is this the last section we'll be covering? Nope, we're gonna do chapter 13 next. But voluntary bias is for those having stronger opinions. They're going to, be like, oh man, sports are great. The problem is doing surveys, you usually get response like this on a Likert scale. And then the people in the middle just don't do your survey. They exist, but the people who are kind of like meh, like with restaurant reviews, you don't see a lot of threes. It's like 5, 5, 5, 1, 1, 5, 5, 5, 5, 1, 1, 5, 1, 5, 1, 1, 1, 5. Because basically someone has a good time or they don't. And the people who are towards the 3 are like, well, it was okay. Imagine that restaurant review. It was okay. I liked it. Didn't like it that much. I don't know. Maybe we'll go back. Just depends. That's the restaurant. I'm gonna write that about. Next time I get a 3, I'm gonna write a restaurant review. Be like, it was okay. Nothing really to complain about, but nothing was great. So, really helpful review right there. Convenient sampling is getting information from the easiest people to access. Think about ways to memorize this. Like convenient means it's easy. Voluntary means people are volunteering. So easier ways to remember those methods right there. Let's continue on to some chapter 13 with what time we have left, because that's a more difficult chapter. So remember, and we'll mark this here, chapter 13, problem 1. Put here. Okay, so I'm going to write a problem right here. What is the first thing we do? It was in the Kahoot when solving a sampling distribution problem. So this is, if you're watching this right now in the future, getting prepared for the test, I want you to look at these steps and then do them on the test. So we have a kind of step before Leo.
Notation wrong.
So we have one step before that. Kyle's got it right there. We'll throw some points. So we're going to get started here. Okay. So here we go. I didn't put all of it yet. Very short, simple question right here, all written out for you. And so we know that UT has 60% of students from Tennessee. And step 0 we should have right here. Good to see you there, George. What is this cat or quant? So is this cat or quant? Categorical or quantitative? Which one is it? It is cat. And the reason it is categorical is think about the question we have to ask. Are you from Tennessee? Great job, Deep, right there. Are you from Tennessee is categorical because it's yes, no. Does that make sense? So it's categorical because it's are you from Tennessee? So we've already answered cat or quant. And once again, try writing these steps for any problem you're doing. Even if it doesn't ask you, it'll help you solve it correctly each time. Check the conditions. Condition 1. What is condition 1? I didn't write them out right here. I need you to help me do the conditions now. You can do notation next if you want, technically. But the first thing is cat or quant, which is very important. What's the first condition? We just showed it on the screen. What's the first condition? Random. So random is the first condition right there. And it states it's random, so we're good. We selected random students. What's the next condition? 10%, which are we good or bad here? So are we good or bad on the 10%? Are we good or bad on the 10%? Are we good or bad? Great job, Savannah, right there. Are we good or bad on the 10%? Are we good or bad on the 10%? We are good. Our sample of 100 students is way less than 10% of all UT students. There's tons more than 1,000 UT students, so we're good on that. Good to see Eric Kyle. And so bring in them. And next we have success failure. Give numeric backing. Okay, so how do we check success failure? Great job, Savannah. Less than 10% of that, Savannah. That is correct right there. Less than 10% of that. So how do we check success failure? How do we check success failure? Give me the numeric backing for checking success failure. And do we have that? We need NP and NQ to both be greater than 10. So if you want, we might need to start marking notation like N is equal. No. We might need to start marking notation right here. And I don't have that. It'll be given later on the problem. So we might need to start marking notation right here, right? So what do we have? What do we have notation-wise? What do we have notation? N is sample size, P is true proportion. Basically. N is sample size, so that is N. And then P is true proportion, given as a decimal. And then Q is 1 minus P. So 1 minus P right there. And there we go, Autumn's got it right there. So N is gonna be 200. P is gonna be 0.60, not that. And then Q is 0.40. So NP is equal to 100. Why did I say 200? It's 100. I don't even know how to do my own problem. And so it's equal to 100 right there, and then we times that by 60, and NP is equal to 60, and then NQ is equal to, you can probably see it already if you know how to do these, is equal to this, and NQ is equal to 40. So we've given the numeric backing, and they're both at least 10, so we are good, because both NP and NQ are greater than 10. As shown right here, NP and NQ are greater than 10, we are good. P hat is given later in the problem. And actually, let's go ahead and mark X right here, because P hat equals X over N. I know I put this later in the problem, but can anyone tell me what P hat is equal to? It is later in the problem, a theoretical P hat. And then we're going to find X here in a second too, to show kind of, maybe connect some dots. Do you see P hat later in the problem around number 4? Where is P hat in this problem here? Where is P hat? I give it later on. Where is P hat? It was later on in the problem. Like it would be multi-stage problem. Then you're like, oh, what about this sample? 70% right here. And so that's what P hat is. And so now you can start to backwork the equation, because think about this. You know that this is, I'm not going to write it, that. And does anyone have any idea what X is? X is the amount of successes. So do you know what X is for this problem? So you can start plugging in numbers, because we know the sample size is 100, remember? We already found sample size is 100. So if we're going to find X right here, what is X, which is amount of successes? What is X? X is what? Type it again real quick. I see some answers, but what is X specifically? X is the amount of successes in a sample. That's what X stands for in this problem. It can be different things like variable X, but in this instance, it means amount of successes in a sample. I hate that we double use things, I'm sorry. It is going to be 70. If you plug in right here, does that make sense? 70 successes in the sample over the 100 sample size is equal to a sample proportion of 0.70. Does that make sense when you see it? Yeah, so just writing the notation right there is a good way to practice. P hat is equal to X over N, where the sample size is 100. We have 70 successes, a sample proportion of 70. Now, I know I used 100, makes it easier on the math. So draw the sampling distribution now. Draw the sampling distribution. First off, if we pass the conditions, what is the shape? What? If we pass the conditions, what is the shape of it? It's normal. Do we need to pass the conditions to calculate p hat? Yes or no? Do we need to pass the conditions to calculate p hat? To calculate p hat, do we need to pass conditions? Yes or no? No, or y bar. There's no conditions for those. No conditions. You just calculate it, the average or the proportion from a sample. So we draw out the distribution right here. And there's the distribution. Oh, better one. There it is right there. So it's normal. The shape is normal because we passed the conditions. So normal conditions were passed. And now what is the mean? You still, oh man, thank you. So what is the mean? Thank you, Kyle, 100 points. What is the mean? It is mu p hat equals to p. So that's what the mean is. It's mu p hat equals to p. And now take a look. We just go up here. And since we know mu p hat equals p, well, the mean, it says what is the mean of the distribution? That is the mean for the sample proportion. It's equal to p. So we just go right here and we put p at the center. It's going to be 0.60. I'm trying to color code everything to make it make sense. That's 0.60, which is mu p hat equals p. The standard deviation is going to be p times q over n square root. And that is the standard deviation of p hat, which is what this one's asking for right here. So we plug in the numbers, p times q over n square root. And what's going to be about 4%, 3%? 5%. Let's call it 5%. Makes life easy. Don't round like this on the test. I did this for a reason, because it makes the problem a lot nicer for what's about to happen. We would have a margin of error that would accept this, I would hope, because this would be a perfect test problem now. Okay, I've written out part of the curve. Notice that this standard deviation is this quantity right here of 0.05. I rounded it a little bit nice and neat. So here's the thing. We would expect you to get a close enough guess that you could get this with multiple choice. Or any questions on this part right here where I found the mean and the standard deviation, mu p hat equals p, and I'll mark other notation right here. If you notice, it really just boils down to notation with p, with q, there's q, there's p, and the standard the sample size. Any questions on this? This says what is the standard deviation, so it's asking that. Questions on this right here? It says what is the standard deviation, which is this quantity. So that is the quantity right here, the variation. And then this quantity right here, mu p hat equals p, well, p is that, and that is the center of the curve right there. Okay, good stuff. First off, mark where it's at on the curve. 70% would be where on the curve. Do you see where it's at? The way I wrote this, oh, that's good, Savannah. 70% would be where? 70% would be where on this curve? 70% would be where on this curve? I'll go down here. Kyle got it, it's 2, z-score of 2. So you can go right here, and I should say find the z-score. That would be first thing, technically. And I'll write the equation for the z-score. So find the z-score. So to find the z-score, we go right here and we do observation minus mean over standard deviation, which we solved a lot of these out, is 0.7 minus 0.6 over 0.05 equals 2. And we go right here and we mark it. So with this being marked on the curve, you can see it's right here. And so the z-score is 2. What was the u in the mean? That was, I drew a little mu p hat equals p. That's the expected sample proportion is equal to the true proportion. I did a u, but it's a mu right there. I should have, Kyle, let me throw you some points, or Colby, let me throw you some points. This right here should be mu. Technically, I should have done better notation on it. That should be mu for true, mean, or expected. We'll go insert right here, just in case anyone's wondering, and symbols, and put in a mu right there. I kind of went shorthand on it. And thank you, Colby, so much. Good questions. And so now, what is the probability, or let's say probability greater than? Give the probability greater than. What is the probability above this? Well, we can use one of our classic rules right here. Let's go to a purple pen and a light purple. I want that one. And with this, we go here, here, 95, and you should have 2.5%. So 68, 95, 99.7, there we go. So it's about 2.5%. Is this odd? It is pretty odd. It's pretty high above what we would expect. So we marked down the distribution. We gave the probability of 2.5%. The z-score is 2. The probability is about 2.5%. It's marked on the distribution with the line. And we did estimate the probability, which I said right there. But that's got it. That's a full solve problem to say that this would be pretty odd right here. So this is a chapter 13 on sampling distribution of sample proportion problem, fully worked out right here. Hopefully it makes sense. It's a tougher chapter. We're going to finish off here with a sampling distribution for the other portion, and we will have done pretty much the full material to a certain extent. So what do you notice doesn't change about this sampling distribution? Going from just data to a sampling distribution, the what always stays the same. Let's look at we're going to go to the next question in a second. But what stays the same between sampling distributions? Like if we were to do the sample mean would have the same what? You're welcome, Autumn. Great job. So the standard deviation gets smaller by a factor of square root of n, and mu, the mean, stays the same. So the proportion as n increases will always stay the same because the true proportion stays the same. So the mean for the distribution of the sample proportion stays the same. So if n changes, it doesn't do anything to the quantity of the mean. It will change the standard deviation. The standard deviation gets smaller and the distribution gets more what? So the distribution gets tighter and the distribution gets more what? We'll do the last question right here. Great job, Savannah. Really good practice. The distribution gets tighter and what else? More normal, exactly. More normal, make sure n is large enough or you have enough successes and failures. And I always like showing this binomial applet. And here's the binomial applet. If you notice right here, we go and we start increasing the amount of successes. Notice it's not normal. With a half a success, then you start increasing and it becomes more normal. Or you could go down here and do something like a sample size of 10. And as you get larger samples and you get enough successes, it will reach normal. When you have at least 10 successes, at least 10 failures, or you meet the large enough n condition for the next one we're going to do right here. So let's go ahead and head into the next question. And we're basically going to do, I'm going to take the question right here and basically use it as the structure for how to solve this. So we're just going to erase everything on here. It's going to be easier to use this than it is going to be to write a whole new sheet, I think. So we're almost done here. Almost done with writing this out. We just have to change some of these questions a little bit. Okay. There we go. And we'll delete this and notation. And we'll keep that. Okay. Okay, first thing we do is a cat or quant. So let me mark this right here. Is it cat or quant? 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 It's quant, yep. Because we're doing things like what is the GPA of students, and that is going to be a quantitative. Great job, Kyle, right there. Quantitative is how much is your GPA? Someone reports that with a number. So quantitative GPA. Now, what did I do here? Notice the first two conditions for the remainder, and Bryce, great job right there. The first two conditions for the remainder of the semester are always the same. Random. We took random students, 10%. We took less than 10%, so we took 100 random students, and we took less than 10% of the university. So the first two conditions are always the same for the remainder of the semester. That's just the way the class works. So you do have to know for this test, QQ, straight enough, no outliers, plot doesn't thicken for regression. But for the remainder of the semester, when we do tests and intervals, it's going to be random 10%. And then we didn't say it last time, but what's the condition, or what do we do here when you get to this? Put them in the chat. Not this, put the other pause in the chat, because you have to think, what variable am I working with? There you go, Kyle knows. Am I working with the cat or quant variable? And so we asked this because right now we have two options here. We have success failure, or we have large enough n. So this is the large enough n condition, which states, and do I still have sheets open on this? Because it's a bit to write out. Let me see if I have it. Let's see if I have a success failure sheet opened up here where I went through it. Wow, that's an old one. Yep. So the large enough n condition states, you know what I'm gonna do? I'm gonna give you a peek at the last video right here where I did it, because I highly suggest watching these videos. So we're gonna self-promote right here. Self-promote the video. We're gonna go over to the live video right here. Thank you to my 8 viewers currently. And if you go over here to the office hours, I believe it should be right in here. Did I not cover it right there? Did I not cover all the conditions? Oh my. I covered on April 1st, April Fool's Day. Give it a second more. There it is, checking large enough n. So this is where you're going to see me go into a longer talk on it, and I have it written out. I'm going to drop the video link in the chat right here. So the way this works is basically the more skewed the data is, the larger n needs to be. And we go through here and we show examples of it where we check the condition by looking at the shape of the distribution. Is this test on 7-8? Yes, correct, George, right there. Make sure to check the link or the review sheet right there to check what chapters it's on. So check the chapters. So right here, you first need to look at the shape of the original data. Then you need to check the size at which you've sampled. Then you need to see, well, what is your sample size? The required size is 1. Our sample size is 2, so we would be good. So in this problem here, what is the shape of the data? First thing to do is check the shape of the data. So what is the shape of the data? The first thing to do is check shape of data. So the shape of this data is what? What is the shape of this data? What is the shape of this data right here? You missed chapter 10 there, George, which is, I just realized you missed chapter 10, which is sample surveys. Definitely check out the review page. It's got everything listed that's on the test, review 2. It's not normal. The shape of the data, don't worry if you get it wrong. Good answer, Savannah, right there. The shape of the data is very skewed. So this data is very skewed. Left or right, Rock knows. As long as it's skewed, we're going to be handling it the same way. What is the required sample size to meet the condition? Oh, no worries. What is the required sample size to meet the condition? We'll be doing more practice tomorrow. Yep. Basically the same thing. I'll probably just make up more questions. So very skewed is 100. Skewed is 25. Very skewed is 100. So there's the very skewed right there. And very skewed, we need at least 100. So we need at least 100. So we need at least 100. Did we sample above at least 100? So the last thing right here depends on what you answered for this one. Did we sample at least 100? Did we sample at least 100? Did we sample at least 100? Yes or no? Did we sample at least 100? Yes or no? Yes, we did. We sampled 100. So n is 100. Well, that's some of the notation coming up. So get ready, start marking the notation for me right here. This is where usually people get stuck. Yep. 14, there's 14. 14 is this chapter right here, actually. This is chapter 14, sampling distribution of sample mean. This is chapter 14, sampling distribution of sample mean. It has other stuff in it too, but chapter 14 is sampling distribution of sample mean. So n is equal to 100. And then what else do we have? This is chapter 14 right here. But I told it 13 in the notes, didn't I? Yeah, let me change that. Close, Savannah, and I'll be very, very exact. But be very, very exact. You're kind of right-ish. You didn't say anything wrong, but let's be more exact. You're on the right track. So notice how we're down here, and you can grab this right here to help with the notation. But you got to be very exact because there's going to be problems, especially working through the problem. So you want to grab your formula sheet when you're marking notation, and you want to mark very exactly what is what. You didn't say anything wrong, really, but we got to be very exact. Very, very exact. We register the... So give it a try. Don't worry about being wrong. You're right so far, but let's be more exact. Well, it is the mean, but in notation, what is it? You are correct. I mean, there's a lot of ways to write it, but specifically from the problem, this quantity up here, very specifically, is what? It's mu. Exactly, that is mu. So we know what mu is. So insert symbol, that is mu, is equal to 3.6. Now, what else do we have? You're on the right track. You're doing everything perfect right now. You haven't said anything wrong. So you're very correct. That is mu equals 3.6. So what next? We're being very exact. Sigma. Exactly. Sigma, insert, great job, Kyle, right there. Kyle points in the chat. Sigma, where's the sigma? Insert symbols, more symbols. Sigma. Sigma. I swear. I'm gonna spend all day finding a sigma. Wish they had a search here. I haven't used it lately. Sigma. Could write it. Looks. There we go. Sigma is equal to 0.1. And then we also have what else? There's one more thing we have. There's one more thing we have up there. Sigma's 0.1. What else do we have? Y bar. Formula sheet will be provided. You need to print it out or you need to write it down. You can only have that JBox. Good to see you there. You need to print it out or write it down. You can't have other things on it. You can do one of those things right there. Y bar, which is the sample mean, because that came from a sample size of 100. Y bar is equal to 3.7. So notice that we have right here, we have already found quite a few quantities here because we know certain things. And we have right here that sigma is this. Here's sigma. And we have right here Y bar, which we'll use later on. Y bar is right there. And we have right here N, which is sample size. We'll go nice orange on that. N, which is sample size, is right here. And we can now find basically this, which that is that. So it's that basically right there. And that is that right there. And then the standard deviation can be found via this. We can solve for that now. So now we go right here. What is the mean of the distribution? So mu Y bar equals mu. So it's asking what is the mean for the sampling distribution. Notice how this says the mean of the sampling distribution. So that is mu Y bar equals mu. And that is equal to 3.6. And this says what is the standard deviation of the sampling distribution. So if we're doing the sampling distribution right here, it's what is the mean and the standard deviation of the sampling distribution. So I hope that was clear in the question right there. I'm writing these out a little bit quickly, and that is sigma over square root of n. And that is equal to 0.1 over square root of 100. And good to see you there, Win. And we're going right here. We're going to solve this. And so now what is the shape of it? By passing the conditions, we passed conditions to see it's normal. What did we need? What conditions needed to be passed to have Y bar? To have Y bar, what conditions? It's like I want you to know this. What conditions needed to be passed to calculate Y bar? What conditions needed to be passed to calculate Y bar? What conditions needed to be passed to calculate Y bar? None. There's no conditions. It's just calculation. You just add things up, divide by how many. So like Y bar is equal to the sum of the observations of Y over the sample size. It's literally just like taking numbers like 4 plus 10 and dividing by 2 to get an average of 7. But there's no conditions to calculate Y bar. The whole reason to check conditions is to see if the data or the sampling distribution follows the normal. So you check conditions to see if the shape is normal. There are no conditions for calculating Y bar or P hat. They're just math. So is 3.7 odd? Well, if you draw the sampling distribution, you'll see it. So I'm going to draw that down here. Is 3.7 odd, yes or no? Who can tell me in the chat? Feel free to say it. Is 3.7 odd? Is 3.7 odd, yes or no? So is 3.7 odd? I'm actually going to have to draw a little bit. Is 3.7 odd? Is 3.7 odd? Yes or no in the chat? Be careful. What's its z-score? What is the z-score for 3.7? What is the z-score? It is. Why is it odd? What is its z-score? Always double check your work because you can get tricked by a question and be like, wait a minute. It's like, oh yeah. Well, what is its z-score? Is it 1? So the standard deviation is this quantity here. Start plugging in numbers. Start plugging in numbers. Solve it out. See if you get what I get. I can't get things wrong. So what do you get? Give it a moment, see if you can get it. Plug in the numbers. I've got things circled. You just have to take the numbers and plug them in. You got 1, but be careful. What did you divide by? What did you divide by? When you divided, what did you divide by? Double check your work here. I can't get things wrong, but I think I've done it right. Be careful, the top of the equation. Check your top of the equation. The top of the equation is where the issue is then. Yep, there it is. And double check, don't worry, this is just practice. Just practice. Yeah, it's way easy to make a mistake. That's why I was just pausing right there, and then I'll help out. Like, I am capable of making mistakes too. Don't worry, you see me make them all the time here. People forget them. They're like, oh, Brian gets it all right. And I'm like, nah, watch, I'll make more mistakes. The answer for the z-score, which is 10, is just ridiculously off the curve. This z-score of 10, so z is equal to 10, is going to be way over here. So the probability, it's even further maybe. The probability or the probability above this is basically what? So the probability is basically equal to what? The probability, Kyle, great job right there. You're welcome. The probability is basically what we're talking about, this area right up here. The probability, which that's the answer if you see what I wrote, saw what I wrote. The probability is basically equal to what? Because it's the probability, it's this area right here, the highlighted area right there. It's so far off the curve, it's basically 0. So basically this is virtually impossible. And this is not the GPA of one student being 3.7, because that's likely. If you draw one student, then you'd have this would be a z-score of 1. But when you do the sampling distribution of 100 students, the standard deviation decreases by a factor of square root of n, making it super duper unlikely. So this p-value is basically 0. Like, it's virtually impossible. And it might not even gone 10 standard deviations above. It might even be further over here to the right. It's virtually impossible. Well, Savannah, good work. We've got this video sectioned out. I'm going to hit the save on this. Really good work. We'll go over to the main screen. This is a challenging test, and basically if you're watching this video, you just got reviews for multiple chapters with example problems. I tried to write out each chapter. Savannah, do you think this helped? Basically, I walked through each chapter how it would solve a problem. We did conditions. If you think where we started, we did regression. We did like multiple choice on it. We did interpretations. Then we did probability questions. You're welcome, Savannah. Really good work. Savannah, thank you so much for being here. I really mean that. It's like, sometimes I have office hours where no one shows and I get sad. I don't get sad much anymore because we have people here. We did probability questions, did a blackjack question there, did sample surveys, reviewed all the different things you should have on note cards, and then we did 2 example problems here. So with that, we'll be back next time. Bye for now.